Let's talk about complex numbers. Now, a good place to start is, where do they come from? Suppose you want to solve this quadratic equation, x squared minus 1 equals to 0. Well, if I solve this a little bit, I get x squared equals to 1. And so to solve this equation, I want to find some number where if I square it, it gets me 1. And we know that for that it would be plus or minus 1. Now, if I change this a little bit and look at this equation, x squared plus 1 equals to 0, right? This one is telling me that I want some number that if I square it, I get negative 1. And of course, there is no real number that does this. So someone invented a number and called it I, and the definition of this number is that I squared equals negative 1. And this was the first imaginary number. An imaginary number is any quantity whose square is negative. So there's a whole bunch of these. Like, for instance, an imaginary number also would be 3i. And so let's call that c equals to 3i. And if I square that, c squared, I get 3i squared. That'll give me 9 times I squared. And of course, we know the definition of I squared is negative 1, so this gives us negative 9. So here's another imaginary number, again, some quantity whose square is negative. We're going to find that quantum mechanics is most elegantly expressed using complex numbers, so they're pretty important in quantum mechanics. Our general definition for a complex number is this right here. We'll usually use C to define it, and it's a combination of two parts. So really a complex number is a way to sort of hold two different numbers. The first part is the real part of C, we usually call that A, and the second part is the imaginary part of C, which we call B. And the way it works out is that if A is 0, your number is purely imaginary, and if B is 0, your number is purely real. You can add and subtract complex numbers with addition. If I have two different complex numbers here, again, a complex number is a combination of the real and the imaginary possible numbers. You just add them up, and here you just literally add up the two real and then add up the two imaginary. Multiplication, a little bit more complicated. So if you multiply two complex numbers, you multiply the different parts just like you would normally, and you'll end up getting something looking like this here. Keep in mind that this includes sort of multiplying this piece times that piece. And so if I do that, those two pieces, I come up with a squared b1 b2, which gives me negative b1 b2, which is this term over here. And so the I squared, you could write it as I squared, but it's just nicer to write it as a negative 1. It makes things a little bit easier. Now, one thing that complex numbers have that you don't have with real numbers is a unique operation that's called the complex conjugation. And it's pretty simple to actually do it in practice. So the complex conjugate is defined as C star. So if this is my complex number, C equals A plus IB, C star is A minus IB. And we'll do some practice with this, but essentially you look at your complex number, and anywhere there's an I, you replace it with a negative I. That's how you do this in simple terms. And it leads us to another new definition, which we're going to call the absolute square. We refer to it this here, C squared. And what this is, it's the complex conjugate of C times C. And so again, if C is my definition A plus IB, then this will be A minus IB times A plus IB. And if we write this out, I get 4 terms. So if I do A times A, right, I get A squared. Then if I do this middle term, I get negative IB times A. So that's that term times that one. And then now if I do A times this guy over here, I get positive IBA. And then finally, my last term will be negative I squared B squared. So what happens is these two middle terms cancel out, and I'm left with A squared. And of course, I squared is negative 1, so you get negative times a negative, and you get A squared plus B squared. It's pretty important that you agree with this, so make sure you go through and can get this. But what happens is whenever we take the absolute square, it's always going to be non-negative and real. As mentioned, our complex number actually has two pieces of information, right? So our standard issue is A plus IB. And so just like a two-dimensional vector, one way to interpret this, a really powerful way to visualize this, is to use what's called the complex plane. And so here our axis, our x-axis is the real axis, and our y-axis is the imaginary axis. And we can just plot this just like it was a two-dimensional vector with the x-axis A, the y-axis B, and they represent our complex number as a vector there. And what's also interesting is if we look here at this absolute square, so again, if we take the absolute square, I get that a squared plus b squared. Well, if this was a vector, right, the length of this vector would be the square root of a squared plus b squared. So this absolute square gives us something similar to the length squared of this vector when you visualize it in this complex plane. One operation that we're going to use complex numbers on will be when we deal with vectors in quantum mechanics. So in quantum mechanics, we're going to set up different vectors that'll represent different things. And these vectors will possibly, their components can be complex. And so basically there's two ways to represent these vectors. The first way is a ket vector, and it's written this way here. And that's going to be a column vector with different numbers of complex components. For us, we'll pretty much only do this with 2 components, but in theory you could do it with more. The reverse symbol here, which is known as a bra, will be a row vector, and if you take the bra of this ket, you'll have the same numbers in there, but they'll use the complex components in this row vector. And what we'll do with these vectors is we'll multiply them together in what's called the inner product. And these names might seem kind of silly, but so this is the bra and this is the ket, and so when you put them together like this, it's a bracket. Is sort of the idea here. And what we'll do is we'll multiply these 2 vectors together. And this takes a little bit of getting used to, but this will be pretty much the only linear algebra type things we'll do, and we're going to go over it right now. And it's basically taking this row vector times this column vector. And when you multiply them together, you'll find that this is very similar to the dot product we've used before with vectors. And so let's try an example here. So here's 2 vectors, u and w, and I want you to calculate the inner product of these 2 vectors, the bracket of UW. So go ahead and think about this. Pause if you want to, and we'll discuss it in a little bit. Okay, so I get the answer to be -4 plus I. So hopefully you got that same thing. So to calculate this, we would write, again, UW. So U is the bra, and so I'd write that bra, and so it'll be 1 minus I, because again we're taking the complex conjugate for the first piece, and then -2 minus I for the second piece. In a case like this, it's maybe even a little bit better to write these in parentheses so you remember which piece is which. And then that'll be times my W, which I don't affect at all because that's the ket. And so if I write this out, when I multiply these 2 vectors together, it'll be this piece times this one. So I can write that as I, 1 minus I, and then I'll have this piece times this piece. So it'll be plus -2 minus I times 2 minus I. And now if I go through and work this out, this piece here I can write as I negative I squared. So I'll keep that as I squared for right now. And then this piece here, if I do multiply this out, I'll get -4 and then negative I times 2, and then plus 2 times I, and the negative sign will cancel for that one, and then plus I squared. So again, I'm just multiplying all the different terms through here. And so we'll find that these 2 pieces go away. Now actually, since I don't even need to plug in I squared, since these 2 pieces will cancel out, and I'm left over with 4 negative plus I, just as we had mentioned. So make sure you go through and do this. When you first do these things, especially if you haven't had much practice with complex numbers, these can be pretty tricky. There's some problems in the book for you to go over, but I definitely advise going over a couple of these. I think once you do a couple, it's not so bad, but these numbers can be a little bit tricky at first. These inner products we have, as mentioned, are very similar to dot products. And so we'll define that if the inner product of 2 of our vectors is 0, we'll call these 2 vectors orthogonal to each other. And furthermore, in quantum mechanics, we're going to like vectors that are normalized. And normalized means that the inner product with itself is equal to 1. Now, here's a student question. Is there a meaning behind the inner product, or is it just a mathematical tool? Well, the inner product is very similar to the dot product that we've maybe used with real vectors. And so let's suppose I have 2 vectors. I'll call it A and B. All right, now we define the dot product to be A dot B. Now one way to represent this is the magnitude of A times the magnitude of B times cosine of the angle between them. all right, the angle between them. Now, if that angle between them turns out to be 90 degrees, you get 0, and so that would imply that the dot product is 0. And that means those two vectors are perpendicular. Well, this is very similar to us calling the vectors orthogonal in our case here. And on the other case, cosine of 0 gives us 1. If the two vectors are parallel. So what the dot product, in a sense, can do is it can give us a sense of how parallel our two real vectors are, right? A dot B, if it's the biggest it can be, that means they're basically parallel with each other. If cosine is 0, and if cosine is 90, it's 0, it tells us that they're perpendicular to each other. And that's what this inner product kind of does with the vectors that we'll be dealing with. It gives us a sense of sort of how similar the two vectors are, with the case of orthogonal being that they're sort of 100% dissimilar. The last thing we want to talk about is, I think, very confusing if you've never seen it before, and this is Euler's formula. This will be very useful to us in quantum mechanics. It will be pretty fundamental. And it's this definition here. So you can think about it either as e to the I theta, so the exponential of a complex number, or if you write it out that way, you can also write it this way here, where it's cosine of that theta plus I times sine of that theta. Now, if you take this interesting formula, it behaves very similar to an exponential function. So here's a couple of things that it does that an exponential function would do just as well. And furthermore, if you look at this, taking the complex conjugate of either the exponential side or of the cosine theta and the I sine theta side gives you the same thing, which is, again, the complex conjugate of e to the I theta. Now, we're going to use this a lot, and so we want to try to understand this a little bit better. And so a lot of times people are like, what? And so what this really is a complex oscillating wave. So we'll show here in a second that as theta increases from 0 to 2 pi, e to the I theta traces out a unit circle in the complex plane with angle theta. So we'll show you what this means. But basically, this is very useful when we want to describe oscillations or waves very compactly, which quantum mechanics, we're going to want to do this very often. So here's what we mean by complex exponential oscillating wave. And so let's start with theta equals 0. So if we plug in 0 for this, we get cosine of 0 plus I sine of 0. So we get 1 plus 0. This is totally real, and so we get this point right here. Now if we look at e with theta equal pi over 2, all right, so cosine of pi over 2 is 0, and sine of pi over 2 is 1, so it gives us I. So now this thing is shifted over here to be at 1 on the imaginary plane. As we go so on and so forth, you can see that it just rotates around. So e to the I pi, well, cosine of pi is -1, sine of pi is 0. So now I've shifted it over here. The same or similar thing with when theta is equal to 3 pi over 2. Okay, if you plug this in, cosine of 3 pi over 2 is 0, sine of 3 pi over 2 is -1, so I get negative I. So this thing is now at -1 in the imaginary plane. And then now it repeats itself. So if I go now to 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0. We're right back to where we started from. So what this has done is it basically traces a circle of length 1 around this plane. And as you increase that theta, as you keep increasing it, it's just going to keep going around. And so here real quick, so it starts here, goes to here, goes to here, goes to here, goes to here, right back to the beginning. And if you just keep doing this, it's going to keep repeating. Okay, so this function, if you increase theta, as you increase theta, it basically oscillates around this complex plane. So we'll keep talking about this as we go on this semester, but it's really good to kind of get start getting a feel for this. Here's some problems you can work on at the end of the chapter for some review, but otherwise we'll talk more about this in class.